Welcome to Green Giants, Titans of Renewable Energy, the podcast where insights and innovation meet. Every episode, we dive into conversations with industry leaders, experts, and change makers, bringing you the stories and ideas in the renewable energy sector that shape our world. And now, let's jump into today's episode with your host, Wes Ashworth. Welcome back to Green Giants, Titans of Renewable Energy. Today, I'm joined by Drew Maggio, Technical Director at Highmark Building Efficiency, a New York City-based firm working across HVAC, electrification, heat recovery, water management, retrofits, new construction, service, and maintenance. This conversation takes us into one of the most overlooked frontiers in the clean energy transition, buildings. Drew sits at the intersection of mechanical engineering, heat pumps, wastewater energy transfer, thermal energy networks, regulatory compliance, and real-world project execution. And what makes this conversation so compelling is that it changes how you see a city. Subway tunnels, sewers, data centers, mechanical rooms, and buildings themselves are not just energy users. They are thermal systems full of wasted heat and untapped opportunity. This episode is about heat pumps, but it's also about something much bigger: how we recover energy we already have, use it more intelligently, and make buildings active participants in the clean energy transition. With that, Drew, welcome to the show.
Thank you for having me.
It's great to have you. Super cool, interesting topic that I'm really excited to get into and dig into. Is not one that we talk about often. It's always loved those as some of my favorite ones, but we'll start a bit with just you and your journey. And I know you spent a lot of your life around physical systems, tools, fabrication, bikes, robotics, construction, mechanical engineering. When did you first realize you were sort of wired to understand how the world works by, taking things apart and putting them back together?
Well, I owe a lot of it to my father. He's a high school mathematics teacher. He teaches calculus and geometry. And then my grandfather was also a carpenter. So growing up, being able to poke through his workshop and see all these tools. And then as I got older, certainly into my academic career, being able to lean on my dad to kind of explain and explore topics like that. I think it was also the show Mythbusters really got me stoked on being able to say like, all right, well, that's how that works. But what if we broke it? Adam Savage has a quote where the only difference between science and blowing stuff up is writing it down. And I don't blow things up, but I love learning about how things work.
I love that so much. I'm a big fan of Mythbusters as well. I definitely watch that a lot, kind of coming up. And it's always a reminder. I've said it before on the show, but parents out there that are in these like cool, interesting technical jobs, like bring your kids into that, help them see that early, develop that curiosity, because it results in like a lifelong passion a lot of times. And you hear that story. So I love that. I love that curiosity and where it all started. What did sort of robotics, machining, and hands-on fabrication teach you about failure that still shapes how you approach buildings and energy systems today?
So I think there's two lessons about failure that, having hands-on fabrication experience is really good for. The first is, mechanical failure. So when something breaks, why does it break? And how can we make that break more elegantly? A common example is on bicycles. You've got something called a derailleur or a gear shifter, and that's what moves the chain up and down all these different gears. And the way that it attaches to the bike frame is using something called a hanger. It's one piece of metal, and it's significantly weaker than the rest of the metal on that bike. And so that's if you drop the bike or if you get into a crash, instead of breaking that really expensive derailleur, just the hanger is bent out of shape, and you can easily bend it back to true. And so approaching mechanical systems and really any engineered system today, being able to take that same mindset of when this does break, how can we make it break in the best way? And so lean on things like redundancy and modularity for swapping out parts. So that's really important. And then I think another thing that you learn about failure is being able to retrace those steps. So failure mode analysis is a very big thing in engineering. And so being able to look at not only engineering decisions, but personal decisions that maybe led you down the wrong path or left you somewhere high and dry. You can look back and say, what are all the decisions that led me to that point? And how can I learn from those and look towards the future? That's the most important part.
Yeah, I love that so much. I think it's such a useful mindset that could be applied to so many different areas. And I think failure is one of those things, like you don't have success without failure. So, honing out on failing well, also learning from it, and some of those failure modes and things like that as well too. So I love that a lot. So your Stevens capstone explored recovering heat from New York City subway tunnels to help cool the subway and decarbonize nearby buildings. What made that problem feel important enough to build a project around and really kind of like then build your career around?
So it's a problem that touches on many factors in day-to-day life here in New York City. There's a sustainable business concept called the triple bottom line that measures a business's impact through profit, people, and then the planet. And so subway heat recovery is a great project that touches on all three of these ideas. So profit, we have carbon cap fines here in New York City for buildings over 25,000 square feet. So there is a legitimate business case where these buildings and their operators are going to be saving money by electrifying and by moving away from fossil fuels. On the people side, 3.4 million people ride the subways here each day. 3.4 million is a little under half of New York City's population. For reference, LA's population is about 3.8 million. So it's almost every single person in LA getting on a train every single day. So with global warming, New York City was actually reclassified from a humid continental climate to a humid subtropical climate. And by the city's estimates, the average temperature in New York City by the year 2080 will feel like Birmingham, Alabama today. So this goes beyond sweating through your shirt or being uncomfortably hot when you arrive at a meeting. People can seriously get hurt by this. We had some stations reaching air temperatures over 110 degrees this past summer, and in the tunnels connecting those stations, it can get up to 120. So it's not just, I'm uncomfortable, I'm too hot. It's people, passing out on a train platform from heat exhaustion. We also had the transit union, TWU Local 100, calling off work multiple times purely because the temperatures were just too unsafe. You can't have somebody passing out from heat exhaustion while they're driving a train with hundreds of people on board. So it's not only a comfort thing, but it's hugely important to safety and the operational efficiency of the train network here. And finally, planet. So subway heat recovery is part of a much larger discussion about thermal energy networks and being able to share thermal energy as a resource instead of just a means to an end. And when you combine all of those resources together across buildings, across systems, you're able to cut down on the amount of energy that you need to put into that system just to make it run. And that's going to give us a lot of benefits when it comes to switching away from fossil fuels to green energy.
Yeah, I love that. Such a powerful entry point into this whole conversation and just connecting those dots. And I love that focus on profit, people, planet, and just the impact. Like, I don't know, not a whole lot of much bigger problems you can solve with a bigger impact. And you can definitely hear your why really strong through that. So before we get into, sewers and subways and data centers and thermal networks, it helps just to kind of establish the foundation. So a lot of this conversation depends on understanding heat pumps, not as a niche, HVAC product, but one of the core technologies that make building electrification possible. So a lot of people hear heat pump and they think, hey, it's basically a boiler, but electric. What's the simplest way to explain sort of why that maybe misses the whole point?
So people will look at heat pumps and say, oh, it's a box that I put in my building, I plug it in and I get heat out of it, the same way that a boiler works. That's just not the case. So a heat pump does exactly what it sounds like it does. It pumps heat from one place to another, much like your air conditioner or the refrigerator in your kitchen, right? Yeah. It's making the inside of that refrigerator cold, and it's slightly warming up the air inside your kitchen in the process. And so that's done through something called the vapor compression cycle. It was first posited in the early 80s. I think the first working one was built in the 1830s. Any air conditioning system that you've ever seen probably runs on this technology. So it's proven tech. It's not some pie in the sky idea that we've recently adopted. All of these systems and the physics behind it have been something that we understand quite well. As it moves forward to the misconceptions about it, if you're moving the heat and you're not generating it in that box, you're simply moving it, then you need to think about where it's coming from, right? And so this is why there's so many different options that people have when they look at heat pumps. They could be geothermal, they could be air source, they could be water source connected to another system. So it's more about understanding that this isn't a box that solves all your problems. It's a tool that can move this thermal energy from one place to another.
Yeah, it's great. That distinction is huge. A heat pump, again, not just making heat, it's moving heat, and it's a helpful way to put it. And I think once people understand the movement of heat, the technology starts to make a lot more sense. So the phrase coefficient of performance can sound technical, but it's central to understanding sort of why heat pumps matter. How do you explain COP so as a building owner, contractor, clean energy professional just immediately gets it?
So COP is similar to efficiency. It's used in a very similar way. It's like an efficiency that can go beyond 100%. Mm-hmm. So with it, for example, a COP of 3 means that for every 3 units of energy I get to move from one place to another with my heat pump, I need to put 1 unit of energy into that heat pump. And so this is to drive the compressor. And when you evaluate these, it's also the controls and the overall efficiency of that system. But at its core, it's about saying how much energy do I need to put in to move this much energy from one side to another.
Yeah, and I hope that's kind of a light bulb moment for a lot of people. Stop thinking about kind of like 80% versus 90% efficiency and start thinking about heat pumps are in a different category and kind of view this differently. So when someone understands that, a heat pump can deliver 3 or 4 units of heating or cooling for every 1 inch of electricity, what misconception usually falls apart first?
So the first misconception to fall apart is that one I just mentioned, that it's a magic box that will solve all your problems and bring your building into compliance. The second misconception that is much more harder to shake is the idea that that system is operating on its own. It's in a room somewhere in your building, and you only have to think about it when you walk into that room. The reality of the situation is that that heat pump is delivering heating or cooling to all of the systems in that building. So all of the floors, all of the occupied spaces, and every other system that that building is made of is going to influence the performance of that heat pump. So a big thing that we're seeing is people not getting that you need to have a well-insulated building. Now, it is possible to install a heat pump into a building that has very old insulation. It's not that the heat pump won't work, but you need a larger heat pump to do that. And so it's kind of like leaving the door open on your refrigerator. If you leave the door open, your refrigerator is going to work a lot harder. You're going to be using more electricity. And if you're leaving all the doors on your building open, you're going to need a bigger heat pump. But this goes far beyond just sizing to the next size up, right? When we look at boiler systems, if your building is poorly insulated, we just grab the next size boiler and maybe you pay a little bit more on your fuel bill, but it's acceptable. When you look at heat pump systems, the difference between a well-insulated building and a poorly insulated building can be tens of thousands of dollars in upfront equipment costs. It can also be tens of thousands of dollars in operating costs for your electricity usage throughout the year. And so we're really trying to get people to understand that the most efficient building is not just one with a fancy heat pump, but it's a well-sealed building envelope that has a heat pump inside of it.
Yeah, and I appreciate getting into that, and just the clarification I think is really important. And speaking of some of those misconceptions, where does this kind of resistance to heat pumps really come from? Is it cost, technical risk, installer familiarity, owner fear, old habits, or something deeper? Like, what is it really from your perspective?
So we've definitely seen cost as a factor that's keeping people from adopting this technology. Not even the cost of just the equipment alone, but sometimes it's the cost of taking that tenant space, out of commission or having to disrupt the flow of tenant activities. New York City real estate is very expensive, and people don't like to hear that, an entire floor or an entire building or even just one apartment would be out of commission for however long a retrofit could take. And so it's understanding that the benefits of installing a heat pump today will far outweigh the cost of doing it today when you compare it to the cost of doing it 5 or even 10 years down the line. I think that installer familiarity is also a very big issue. The cost and having to disturb tenant spaces is a bigger problem on the HVAC side of things. But when you look at plumbing for generating domestic hot water, installers are not always very familiar with this technology. Plumbers have been doing things the way they've been doing them for a very long time. Plumbers are incredibly smart. I'm not here to knock the plumbing trade. You look at the way that they do these piping layouts, and it really takes, an artist to figure out how all of this is going to go together. But plumbers also work on gas lines, and New York City is phasing out gas lines. You can't install new gas lines in New York City. So the idea that there's this new technology and it's eating into your scope that you can bid on, and you need to get all of your people retrained to do these new installations, it's definitely a hurdle. And so we've been working with some organizations here in New York City to try to empower these plumbing contractors to take on these new projects.
Yeah, I like that. Those are really important points to me. And I think understanding the resistance and where some of that comes from, it really helps us start to get to the solution and a better version of that, where people are more comfortable and don't have those hesitations. What do you think? So thinking about just the greater renewable energy industry, what do you think we tend to miss around when we focus heavily on generation, which again, it's important, not taking anything away from that, but pay maybe less attention to how buildings actually use energy once it arrives?
Yeah, this is an awesome question. When you look at the efficiency losses all the way from generation to distribution, maybe storage along that chain, and when that energy finally gets delivered to the building, making that building 10 or 20% more efficient is actually very impactful because all of those efficiency losses leading up to the building will compound, right? And so we can make all the buildings in this city 10% more efficient. That's going to mean that we have a lot more than 10% in energy saved that we need to deliver. And so it's great to have extra efficient solar panels and super high efficient transmission, but we're setting the bar a little too high if we don't look at where this energy is actually being used and how we can efficiently use that energy at the end of that chain.
It's exactly the connection I want listeners to hear. Clean generation certainly matters, really important, but so does reducing waste on the demand side. And, it's a great reminder. Every unit of energy saved inside the building reduces pressure everywhere else in the system. And if we're kind of seeing these demand spikes and growth happen, like it's going to become even more paramount and important as we go to attack both. It's that and not or, as I commonly say. In dense cities like New York, what makes building electrification harder than simply just swapping fossil fuel equipment for electrical equipment?
So New York City's density really lends itself to the price per square foot here. Sometimes these systems will take up more space than boiler systems. Sometimes these systems have to get installed on the roof where, maybe you were going to do an amenity space or a pool, but now you have to put those air source heat pumps on the roof. And so I think just the price per square foot is a very big one here. Geothermal is an excellent option if you don't have that roof space. But if you've ever seen New York City streets torn up for construction work, it's spaghetti down there. There's so many utilities, gas, steam, sewer, subways, electricity. It's a rat's nest underneath all of this concrete. So geothermal sometimes isn't that practical either. So it's really understanding where your building is, what your building needs, and then looking around for, what are my options here, right? Maybe I can do a mixture of geothermal and air source heat pumps, or maybe I can find clever ways to recover that energy either within my building or maybe in the building right next to me.
So yeah, I think New York is such a great test case because of all that you mentioned there between space codes, old infrastructure, tenant needs, grid constraints, all colliding at once. So I'll ask you this. So what really separates a good heat pump project from a bad one?
What separates a good heat pump project from a bad one really comes down to all of these different stakeholders in the design process, understanding what the technology is and how it should be applied. So a quick example would be New York City gets down to 0 degrees in an average year, maybe less than 10 hours out of the year. So 8,760 hours, 10 of them are actually at 0 degrees. But if you're building a building or you're designing a building, you're taking on liability and saying, this building's going to work. Your tenants are going to be nice and warm, even when it's 0 degrees out. So we see a lot of people say, I want my heat pumps to work at 0 degrees. Now we can do that. That's not a limitation of the technology. I can absolutely design a heat pump system that works down to 0 degrees. The question is, how much more heat pump is that compared to a system that's sized for maybe 17 degrees or 25 degrees? What's the difference in upfront cost of the equipment or the installation, right? And so it's understanding that you don't just set your heat pump to the worst case scenario. You're saying, what's the plausible worst case scenario that I want to be operating at? And then just making sure that you have the proper redundancies in place. The New York City Energy Efficiency Code recommends that you use 17 degrees as that benchmark. So when you go below 17 degrees outside, you can use electric resistive heating. If you're above 17 degrees, you're really supposed to be using, a heat pump system. And so switching that design day condition from 0 to 17 degrees, that can be, 20 or even 30% savings on just the upfront cost of equipment. And maybe 10 hours out of the year, you're a little bit less efficient. But if that's what gets the project across the finish line, then you should absolutely be looking at that.
Yeah, really useful to hear and good context there. So we've kind of talked through it a little bit, and I wanted to just make sure we understood heat pumps as heat movers and some basic knowledge there. I think once we understand that, the city starts to really look different. And if heating and cooling are about moving thermal energy, then waste heat becomes a resource. And so when you think about New York and sewers and subway tunnels and data centers and buildings themselves, they stop looking like isolated systems and start looking like pieces of a larger, urban energy network. And so once you start looking at that, so you start looking for wasted thermal energy in a city, where do you see it hiding?
I see it hiding everywhere. You can walk down any street in this city, and if it's not a really hot day like today, you'll probably see some steam rising up out of the sewer system. So these opportunities for heat recovery are essentially limitless. You have the sewer system, which is always at 70 degrees, as opposed to geothermals typically dealing with ground temperatures at 50 degrees. You've got the subway system, which has tons and tons of heat, both from the electrical systems and the air conditioners on the train cars themselves. And then looking around at all these buildings, a lot of these buildings have cooling systems that operate year round. Even in the winter, you need to be dehumidifying the space that people are inside of and breathing air and exchanging moisture. And you need to be able to cool to dehumidify. So there's a lot of places where people are just spitting this energy out into the atmosphere because they want their building to be cold, but that could be a resource.
Yeah, it really changes how you look at the built environment. Suddenly the city is full of energy streams that we usually just ignore and don't think anything of. And so I really like that framing. And it's a good reminder, like the opportunity is not always somewhere new. Sometimes it's already just running underneath us or around us. But this is great. So for listeners who have never heard of wastewater energy transfer, and how can sewage become maybe a useful heating and cooling resource without the obvious, ick factor getting in the way?
So wastewater energy transfer is a great technology that taps into the thermal energy inside of water you've already sent down the drain. This is super applicable to multifamily buildings, but you can also do it on a whole neighborhood or citywide scale. It's been done in a citywide scale in Vancouver, where they have a centralized wastewater treatment plant. They are pulling the energy out of that wastewater using heat pumps to make hot water or cold water, and then distributing that through 60 kilometers of piping to a couple thousand homes and local businesses. You can also do it on the building scale, where you have a tank that collects that wastewater before it leaves your building, and then you're able to exchange heat with that. There's definitely an ick factor. I want to be very clear. The wastewater never actually touches the hot water for your sinks and showers and the next day. It's just the heat we're pulling out of it. And so we do this with some specialized equipment that processes that wastewater so that it can safely pass through a heat exchanger. We then have a special heat exchanger that's designed to allow that kind of chunkier, fibrous flow. And then all of that is exchanging heat to a heat pump system. And then the potable water is on the other side of that heat pump system. Yeah. So if you actually look at the chain of where that energy is flowing, the wastewater is a good 3 or 4 steps removed from the potable water. Now, storing a large tank of wastewater on the premises, definitely a concern for some people, but the technology's come a really far way, and we have plenty of safeguards and other features in place to make sure it won't be an issue.
Yeah, the explanation helps a lot. The key is that you're recovering heat, not bringing wastewater into the building system. Definitely probably a misconception that needs to be cleared up there. Just, New York City, as we talked about, we know has a huge sewer network already connected to buildings. Why is it such a large opportunity? And then why has adoption been so slow?
So it's a very large opportunity because every single building is connected to this wastewater network. In addition, there's also wastewater recovery facilities inside the city limits. So we're not just piping it down over to the next county. There's about 14 different resource recovery facilities that the New York City DEP operates. And some of those are excellent sources of all this thermal energy that we essentially just pile up over there, and then we don't even touch it. As far as the adoption, it's been a little bit tricky because right now you're only allowed to use the wastewater inside of your building. So as I said, the New York City DEP, Department of Environmental Protection, they're in charge of making sure that everyone's drinking water is safe. And a great way to accomplish that is by knowing where everyone's wastewater is. Right now, you're not allowed to pull that wastewater from the sewer main on the street into your building. You can only go one way, and that's out of your building into the main. If we could get a pilot project approved by the DEP to showcase a building taking that wastewater onto its premises, pulling a little bit of heat out of it, and then sending it back out to the sewer main, I think that would really drive adoption.
Yeah, I agree. I think this tension is fascinating. The resources there, but the market still just has to get there and maybe isn't ready yet. Do you see that as like that should happen? Like, are there any downsides of that? And I guess, what would prevent that from being just something that they move forward with and obviously tap into a lot more opportunity here? What's holding it back? Is it just unfamiliarity or something else?
Well, practically speaking, as I said before, there's a lot of stuff underneath these city streets. So it could be very difficult to find a location where that actually is practical and you can excavate and clear everything out in such a way that it will all fit. I think another part of it is, the liability, right? Like the DEP says we're going to make sure everyone's wastewater stays in our system so that it can't contaminate your drinking water. The second you let it go out of that system, now that liability is on the building owner and not the DEP. And so there would have to be very strong contracts in place there, not just for the building's operations, but for the public safety. I think another thing that we should point out is that it doesn't need to be all or nothing, right? We don't need to go to every single building and tap into the sewer main out front of every single front door. I think a better option would be looking at where these centralized recovery facilities are already in place and operating and saying, okay, where can we use that heat that's nearby, right? So there are a couple locations that have maybe public schools or affordable housing nearby. And so if we can use that heat to then reduce the operating costs of those buildings, then sewer heat recovery makes a lot of sense. One great example is Riverside State Park, which is a large state park on the upper west side of Manhattan. And underneath it is a wastewater recovery facility. So it's kind of a two-tiered system. The upper platform that the park sits on is about 50 or 60 feet above the wastewater recovery facility. And they have, I think, a 400-seat theater, a 200-seat restaurant, and an Olympic-sized swimming pool. That requires a lot of heat. And so if we could just knock on that basement, drop a pipe down, and set up a heat exchange system, I think that would be a home run of a project.
Yeah, absolutely. It seems like a huge opportunity there. And we've seen some of this, like cities like Vancouver, Toronto, Seattle, Denver. They have moved further ahead with wastewater and district scale thermal ideas. What are they seeing that maybe New York hasn't fully acted on yet? Like what's attributed to sort of those success stories in those cities?
So in all of those success stories, you've seen the local government in those cities come out and say, we identify wastewater as a thermal resource. We think it could be very helpful to our constituents. And we're going to release either a roadmap or a guidebook or a rule book saying, if you want to do a pilot project and you want to interface with the city sewer system, here are the proper channels and here's how to go through with it. Vancouver especially did this. They have a number of what's called neighborhood energy utilities. And so they're all operating inside the city limits of Vancouver. And if they want to tap into the sewer system, they go to the city and they say, we want to use the sewer system here. The city can review that and ultimately decide if that project would be beneficial. And then they can empower people to use that technology.
Yeah, it's helpful context. And I think it's nice to see the success in some of these other cities. And I think obviously that helps cities like New York and others when you see, like, sometimes people don't want to be the first one, but then they're like, hey, it worked here, it worked there. We've got good success stories and points to look at here. That can help adoption as well. I'll move on a little bit just to subway heat, because I think we've touched on that a little bit. It's fascinating because it's not just wasted energy. It's also a comfort, health, safety, reliability issue. How does that change the way people should think about heat recovery? And I guess too with that, and I'm sitting here curious as well, and I'm sure listeners are, when you talk about subway heat, transferring it, creating it as an energy source, like how does that actually happen? Like what happens in layman's terms? And just talk to us a little bit through that.
Yeah, absolutely. So I think it's helpful to start with how this reframes the way that we see energy moving around us. When you have a boiler and you need to provide heating to an apartment, you turn the boiler on, you make hot water or steam, you send that hot water or steam up, and it's a means to an end, right? You're using that as a tool to move heat somewhere. But once you get that apartment up to a comfortable temperature, you don't really care about where that energy goes. As we're moving to heat pump systems, we have to stop thinking of that as a means to an end and as a resource to be used and applied properly. And so being able to look around and see all of these thermal energy sources and think of them not as pains or hurdles, but as opportunities is really important for framing this discussion and being able to see the kind of projects that are possible. As it moves forward with how this actually happens, that gets a little bit trickier. I'll start with like the easiest, lowest hanging fruit, and then we'll talk about some of the harder applications. The low hanging fruit in New York City is what's called the Second Avenue subway extension. So I'm sure you've all seen the pictures of subway grates on the sidewalk. Subway car moves through the station, pushing and pulling air out of its way, and then you get the wind blowing up out of the sidewalks. The subways on the Upper East Side of Manhattan, because of Manhattan's topology, it's very hilly in that area, there's actually about 100 feet between the sidewalk level and the grade that the rest of the subway system is on. And so to get passengers from the street level down to those subways, they need to use escalators and elevators and build out these subway stations. Now that you have all of these people 100 feet below ground, you need proper mechanical codes. So you need forced air ventilation, you need cooling and heating systems. And so all of that has resulted in essentially a bunch of fake buildings that there's cooling equipment hiding inside of them, and they're piped directly down to the subway. So the project I did at Stevens Institute of Technology, we looked at one of those buildings. We identified some other buildings nearby that were going to be receiving local law 97 fines and having a hard time switching to heat pumps off of fossil fuels. And we said, hey, what if we just, put a pipe through this wall right here and delivered you 90-degree hot water whenever you wanted it? That was the concept right there. So it's being able to say, where is that heat available? And then where does that heat need to go? Or who's going to benefit the most from being able to access this heat? And after that, it's just looking at a map, finding opportunities that are close to each other and trying to get them in touch. The harder stations are all of the older ones because they're difficult to heat and cool the same way a parking garage is, because they're open air. You don't just have doors and windows you can close. And so the heat in there is not just in the air in those stations, but it really soaks into the walls and the floors and the dirt surrounding those stations. So that's definitely a trickier application of subway heat recovery.
Yeah, absolutely. I appreciate you going through that. It's good to just kind of get this mental picture and understand like what's actually happening. How does this work? The other thing, that it's obviously getting a ton of press right now, we're seeing all the time is just around data centers, and they're driving huge conversations around power demand. They also reject a tremendous amount of heat. How should the building efficiency world think about data center just waste heat, and how does that connect?
So anytime that you have a data center that's giving off a lot of this excess heat, that's an opportunity to not only provide that heat to, a building or organization that might need it, but you could also turn it into a revenue stream,
Yeah.
right? You can essentially play as a small utility company and offer that heat at a certain price per therm that would be very competitive with steam or even oil costs. And so anytime you have those loads, you should be trying to think not just how do I get this out of here as quick as I can, but what can I do with this and where can this be used? A perfect example is in multi-use buildings, right? So you've got buildings with residential on the topper floors and then maybe office or commercial on the lower floors. Sometimes, because of the offices, these buildings even have data centers inside of them. So those data centers, no matter what temperature it is outside or how hard the sun is shining, are going to be creating heat, and the building needs to get rid of that heat. If we can use that heat to warm up the water for people's sinks and showers, then it's kind of a double whammy because you're solving the problem of where do I get the heat for these people, and you're also solving the problem of what do I do with all this heat from the data center. So anytime you have an opportunity to connect what we call a heat source and a heat sink, you can make that building overall much more efficient.
Yeah, it's a great connection to the broader sort of energy conversation right now. And data centers are not just electric loads, but they're also thermal assets. And I like it reframes the problem. The question is not only how we power data centers, but how we use what they throw away, and like using this wisely. It's a great business decision. It's a great climate decision, and great all around. So it seems like that's a no-brainer for me kind of looking at it. The next layer I want to kind of get into is scale, and a single building can recover heat, but the bigger opportunity may be just connecting buildings, sources, and storage into shared thermal infrastructure. And that's where the thermal energy networks, geothermal, thermal storage become especially important. The thermal energy network can sound abstract. And what's the clearest way to just explain the concept to someone who understands maybe the electric grid, but not thermal infrastructure?
Yeah, so thermal energy networks are essentially pooling everybody's thermal resources together. So if you think about an electrical grid, most of us are taking energy off of that grid, but maybe I have solar panels on my house and I can give back to that grid. The same way that you're pulling or pushing electrical energy, you can do that with heat. And so the real beauty of thermal energy networks is that once you get enough different nodes on that network, and you can have diversity of use cases and building types and thermal loads, then they can all kind of support each other. So a great example of this is maybe you have a data center on the edge of a town, but you've also got plenty of residential buildings. And then maybe you have a gym and a supermarket and a public school and a hospital, right? If you try to match up each of these buildings one and one and create these nice little pairings, you're never going to get a perfectly matched balance of I'm getting rid of heat and I need to bring heat in. But if you can connect all of them together, it stops looking like, where do I find someone to take this heat away from me? And it just turns into there's a system right here I can dump that heat into, and someone out there will use it. And so then it becomes not how do I supply or take out enough heat, but it's just how do I maintain, a proper ambient loop temperature between all of these buildings. And so that looks like using a centralized system or a distributed system to maintain that loop temperature instead of driving heat in and out of it for the purpose of pushing it to a certain destination.
Yeah, absolutely. It makes the idea much more accessible. I think the comparison to the grid is useful in a way of like we're used to sharing, electric infrastructure, but not always thermal infrastructure. So I just frame it up in a way that we get and we're used to. So let me ask you this. What conditions need to be in place for a thermal energy network to actually pencil out, whether it's density, load diversity, ownership alignment, public policy financing, or something else?
So load diversity is especially important because you want to make sure that anytime someone does or doesn't need that heat, you've got someone else that's willing to take it or give it away. And so matching up all of these different loads gives essentially a much rounded load profile across the entire network. And that's easier to maintain. As far as public policy, it's very important that we make these systems not only accessible, but possible to build. The Public Services Commission of New York State, as part of the UTENJA, or Utility Thermal Energy Network and Jobs Act, requires the largest utility providers in the state to do thermal energy network pilot projects and then report those findings to the state. So this is not pie in the sky. Maybe one day we can all share energy like this. They're building these projects right now and learning from them so that we can have an accurate framework from the utilities and regulatory side to allow these systems to operate. It's very hard for somebody that just owns one building to say, I want to supply oil and gas, or I want to supply steam to all of these people around me. If they're doing that with electricity that's generated on site, it's typically through a utility grid that's already in place. And so it's very hard to essentially break onto the utility scene and say, hey guys, like I'm a utility provider now. And so having a framework in place that enables these groups to come together and build these systems is super important. Massachusetts has done something recently where they're phasing out of gas, and they've essentially said the utility providers, along with the state, are going to residential neighborhoods and saying, hey, do you guys want to be on a thermal energy network, right? No one ever calls up their local government and says, well, why don't I have a gas line in front of my house? It's already there. And so if we can make thermal energy networks as accessible as gas infrastructure is today, then it's less of a big ask and more of a no-brainer.
Yeah, absolutely. I like those comparisons and just the context there and just really understanding kind of like the challenges and the problems, but also like the real, like it's happening and this is coming and starting to come together and you're starting to see it, not just like a pie in the sky idea, but this is, we're actually in it and starting this process. Thinking about thermal storage a bit, doesn't get nearly the same attention as batteries. So we hear tons about batteries and different storage products all the time. But why does storing heating or cooling matter as more buildings just electrify and start to electrify?
So thermal storage is going to allow you to take some of those peak thermal loads and store that energy you'd otherwise be getting rid of. And then you can distribute that as necessary. I think that your listeners are going to be familiar with the duck curve, which is the big peak in electricity demand, and how generation doesn't always match up to that curve. We don't have a daily duck curve with thermal energy. We kind of have a yearly duck curve. And so we need a lot of heat in the wintertime, but we need to get rid of a lot of heat in the summertime. And so it would be great if we could build a huge geothermal plant to store heat for 6 months at a time. But really, really big projects like that can be unpractical. A better thing to do would be looking at the different loads that we can maybe pair up that just don't match up on the time frames, right? And so if we're making a lot of domestic hot water at night, fill up our plumbing tanks and get ready for the day. And then during the day, we have a lot of cooling going on because the sun is shining on our buildings and heating them up. Then being able to cool the building in the day, store that heat, maybe for 6 hours, maybe for a day, maybe for a week, and then deliver it when it's needed, does essentially the same thing as storing electricity. The difference there is that you don't have to actually run the equipment because you've already stored that as hot or cold.
Absolutely. I think it's such an important parallel and should resonate with our listeners as well, as you said. So thinking about solar, just that journey. So solar became far more scalable once storage became part of the conversation. Is building electrification heading towards a similar moment where heat pumps, thermal storage, and flexible loads have to be designed sort of together and viewing it in a similar way?
It's similar, but I wouldn't say that they're exactly the same. I think that electricity storage has made renewables a lot easier to use because the sun isn't always shining, the wind isn't always blowing. And so being able to carry over those times where you have not as much of that resource and still provide the necessary services, that's very important. When you look at how a building operates, it's kind of a given that you're going to be able to have electricity and water and things like that flowing into that building. So it becomes less about how are we going to get through, those dry periods where we don't have any generation, and more about if we can store this energy, are we going to be able to use it? And so maybe that can look like ice storage, where if you need to cool a bunch of computers, you can essentially make ice at night when the outdoor temperatures are lower and it's easier to make ice. And then you melt that ice during the day to provide cooling. So thermal energy storage is very important, but I don't know if it's going to have the same kind of unlocking capacity that electrical storage had. That being said, being able to store thermal energy and then pull it back out when you need it is much more efficient than just running two different pieces of equipment depending on where you need that heat to be.
Yeah, I appreciate the clarification and viewing it in that way as well too. And as we kind of talk about all this, it's exciting, but the real test really becomes where these ideas can really get built and scaled. And I think your work is especially valuable because you sit so close to the boundary between innovation and implementation. where an idea has to survive, codes and financing and contractors and commissioning and long-term maintenance, all those sort of things. So some of these ideas can sound a bit futuristic to people that haven't heard it, but your job is to help turn them into real projects. So what separates a visionary building technology from one that can actually survive codes, contractors, financing, and operations?
I think what separates a practical technology from a more visionary technology is being able to say, we've got this ready and available for the market, right? It's one thing to say, we can build you a machine that does X, Y, and Z, or we could build this whole system. It's another thing to have an engineer call you and say, hey, I have a client that wants to do X, Y, and Z. Are we ready? Are we good to go? And so then it's less about like, does the physics of it all work out, and more about, can we get ETL or UL listed? Is the fire code updated? Recently, we switched over to lower GWP refrigerants. Some of those refrigerants are also more flammable. So now it's a huge upheaval of the fire code and the mechanical code to make sure that these systems are installed safely. And so it's less about making sure that the physics work and more about, can we maintain compliance with the code while still using this technology? I think that cost is certainly a factor to consider here, but we're at a point with these technologies where using them can actually recover or negate costs elsewhere on building operations. And it's very rare for technologies to come around where it's not just a better pencil or a more efficient light bulb. It's something that really changes how a number of these systems work together.
Yeah, it's a really grounded way to think about innovation. And it's always a reminder that best technology is the one that people can actually install, surface, and trust, and jumps through all those hurdles as well. Highmark specifically brings just a wide range of building efficiency technologies into the New York market. How do you decide whether a technology is truly ready for a place as complex as New York City? Like, what goes into the thought process?
So a lot of that process is focused on New York City more so than the actual technology at hand. New York City is a very interesting landscape when it comes to these systems because we've had a natural gas phase out, because the price per square foot is so high. And so it lends itself to certain technologies that maybe in other parts of the world you wouldn't see take off as much. I think when we look at it, the biggest thing for us is, does it make sense from a science point of balancing the energy and balancing those loads? And then it turns into, how are we able to communicate this to engineers and architects and building owners and really show what this technology is able to do? When we look at something that has the potential to change the way that people are doing things and change the way that people think about energy or these systems in their buildings, that's a really good sign for us. That's something that we're really interested in. We don't want to just represent catalog products. We don't want to just say like, oh, you have a Kleenex, I have a Kleenex too. We want to really look at systems that change the way that people think about energy in our city. And then at the end of the day, it's about the cost of installation and the long-term ownership cost. If we can show that maybe it's not what you're used to, but over the next 5 or 10 years, you're going to use less energy and that's going to turn into savings for you, that's a huge part of it.
Yeah, I love that so much. And as we said earlier, so New York is a serious proving ground. If a technology can work there, it says a lot about its readiness and effectiveness. So let's zoom out a bit. If we look ahead 10 years and think about the future and what that would look like, what would New York City look and feel like if we took heat pumps, waste heat, wastewater energy, thermal networks, and building efficiency as seriously as we take new energy generation?
I think if we took all of these concepts very seriously and really leverage the available technology to build out thermal energy networks, that would have so many different impacts across all aspects of life, right? Anytime you walk into a building, maybe it would be nice and cold in the summer because they're not worried about their electricity bill. Anytime you go into the subways, you won't be sweating through your shirt because hopefully, we figured out a way to cool them. I think that a big part of it also speaks to affordability, right? When we look at the New York City Housing Authority or affordable housing projects, these are already hard projects to pencil out. So we can go to these projects and say, hey, it might be a little bit more expensive up front, but over the next couple of years, your operating expenses are going to be so much lower, then that can actually make or break a project. And I would love to see in New York City where we're able to build more affordable housing because of these technologies.
Yeah, a really compelling vision. I think beyond everything else, cleaner buildings and less wasted energy and smarter infrastructure, and a city that uses what it already has as well. And you talked about the cost implications, all those kind of things too. So great vision as well. I love ending there because it makes the future feel practical, not just more technology, but a better designed city. Drew, this was really an outstanding conversation. thank you for taking us into a part of the clean energy transition that doesn't get nearly enough attention. For me, the big takeaway is that decarbonization is not only about building more renewable generation, it's also about recovering energy we already have, using it more intelligently, and rethinking buildings as active parts of the energy system. Heat pumps, waste heat, wastewater energy, thermal networks, and thermal storage may not always get the same headlines as solar, wind, or batteries, but they're going to be essential if we want cleaner, more resilient, and more efficient cities. To our listeners out there, thank you for joining us on Green Giants, Titans of Renewable Energy. If this conversation helped you see buildings, heat pumps, or cities differently, share it with someone in your network, subscribe, leave us a rating, and keep helping us bring more people into the conversations shaping the clean energy future. And with that, we will see you soon.
This episode of Green Giants, Titans of Renewable Energy, was brought to you by Lee Group Search. If you enjoyed today's discussion and are looking to recruit top talent for your company or find your next career opportunity in the renewable energy sector, visit leegroupsearch.com. Let's continue driving the future of clean energy together. Until next time, keep pushing toward a greener future.